isn't as much you have to deal with. But it might not have saved that video from earlier. We'll go through it again. All right, so oxidizer or oxidizing agents. Oxidizing agents want electrons. And so in a redox reaction, we call it electron transfer reaction. Acid-base reactions we call proton transfer reactions. So these are proton, because H plus is the hydrogen ion is a proton. So it's just H plus transfer for Bronsted. There are other types. Redox we call electron transfer. And so basically the oxidizer wants electrons, always wants electrons. So these are electron poor. Electron poor. Sodium, on the other hand, we call sodium the reducer, because sodium was oxidized, chlorine was reduced, and so it's flipped. It was oxidized by the oxidizer. When chlorine was reduced, it was reduced by the reducer. The reducer does the reducing. The oxidizer does the oxidizing. And so people always get this mixed up. And it's very confusing, so you have to go through it over and over again until it clicks. And eventually when it clicks, then it's pretty straightforward. But, there's no charge. Normally we don't write a 0 here if there's no charge. There's no charge, it's new. But this is just to emphasize that. And so sodium was oxidized by the oxidizer. Chlorine was reduced by the reducer. Well, who's a reducer? In this case, the reducer, or reducing agent, which I abbreviate RA, sodium. And so reducing agents, the best ones are electron rich. The best reducing agents are electron rich. Electron rich. And so we'll take a look at as we go along here. And so what we're going to do is we're going to look at the redox properties first. Of these. That way, as we go along, we can learn more. But there's some things to learn. So when we have a formula, analyzing chemical properties. Yeah, it's not just chemical properties. I should put physical properties, but physical properties are a little bit more tricky because you need to know a little bit more about the structure in order to get it. So we can make some inferences, but it's not always accurate. And so let's take a look at some of the chemical properties of these. For example, metathesis. I'm gonna actually jump ahead so that we get more practice when we're looking at all these. And so some of this is not going to make a whole bunch of sense, but what we need is in metathesis reactions, we need some kind of driving force. And so we're going to be looking at different compounds, naming them, and then looking at some of the properties of those, the chemical properties. And so when we're talking about a driving force of a reaction, and something has to happen. And so the driving force is, for example, precipitation would be considered a driving force, because precipitation is the formation of a solid lattice structure. When you form that precipitate, it helps stabilize. This is still not connecting. Okay, so what precipitates? How do we know? How do we know? Well, the way we know is by memorizing the solubility rules. We check what's called solubility. Solubility is, does it dissolve in water or not? If it dissolves, yes, then we say it's soluble. If it's no, then we say it's insoluble. If it's a little, then we say it's slightly soluble. These are what we call qualitative measures of solubility. We also have quantitative measure of solubility. And the quantitative is to actually measure how many grams dissolves or how many micrograms or milligrams dissolve. And so if we want a quantitative measure, then we need the number of grams, milligrams, micrograms that dissolves in a given amount of water. Usually the given amount of water is 100 milliliters. So in 100 milliliters, how much of the solid dissolves? That would be it. So for example, table salt. Is there any limit to how much table salt you can dissolve in water? There is. You know, if you try to make the saltiest water you can, you're going to hit a limit, and that limit is about 36 grams per 100 milliliters. If you try to go over like 38 grams, you aren't going to get all of it in water. It's impossible. And so that's called the solubility limit. However, there's some things that have no solubility limit. You know, if it can dissolve, any amount can dissolve without limit, then we call it miscible. So this is the max. Those are the max. This is grams, milligrams, or micrograms, etc. And so this is the max amount that will dissolve. In a given amount of water. Now, if there's no max, let's say if infinite, then we call it miscible. Like for example, water dissolving in water. Is there any limit to how much water I can add to water? There's no limit. Water is what we call miscible in water. You can put any amount in. But there are chemicals that are very similar to water. One chemical that's very similar to water is called methanol. Methanol, there's no limit. You can add as much methanol to water as you want. In fact, pretty soon there's so much methanol, it doesn't even look like water anymore. It looks like methanol with a little bit of water contamination. That's it. And so those are miscible. So I'm really jumping ahead here because this takes some practice to do. And like I said, the more practice we get, the better, and the easier it will be. And so we have some simple solubility rules. Right. A, for molecular compounds, the solubility rule is like dissolves like. And so certain things would be like water. So for example, if I look at, say, sugar and water. Sugar dissolves in water because they're similar. What is like is we call this a polar substance. We'll talk about polarity later when we get to structure. We will discuss later. And so sugar and water are alike in that sense. However, oil and water are not. If I tried to dissolve oil in water, these are dissimilar. Oil is what we call non-polar, and water is what we call polar. And so this is going to rely on some structure. We're going to dig deeper into structure later, but for right now, this is it. And so if they don't really dissolve in each other, then they're dissimilar. If they're similar, they will dissolve in each other. Like water. Water dissolves in water because they're the same thing. They can intermix no problem. But some things don't intermix so well. Like oil. Oil does not want to mix with water. So that's for molecular compounds. Again, we'll discuss this later because we need the structure of molecular compounds. But for ionic compounds, we can discuss it now. These solubility rules are in your supplement, lab manual. These are very qualitative. These aren't quantitative at all, and there are exceptions. It's not a law. These are rules. Rules are tend to have a lot more exceptions than laws do, for sure. Now, for ionic compounds, you first look at the cation. First, look at cation. Now, this is a physical property, not a chemical property, but this gives us insight into chemical properties here. So we first look at the cation. When we look at the cation, if it's a group 1, what is group 1? Group 1 is the first column of the periodic table. Group 1 and ammonium salts. What is a salt? A salt is a compound of a cation and an anion. That's not an acid. If the cation is H+, then we call it an acid. If the cation is anything else, we call it a salt. And so group 1 and ammonium salts are soluble. So it doesn't really matter what it's attached to. And so let's look at some examples here. An example would be, how about this one? Ammonium, what's this one called? This one's called ammonium or triammonium phosphate. Which one? Triammonium or ammonium? Ammonium. This is ionic. Even though this is all non-metals, we still consider this an ionic compound because of the ammonium cation and the phosphate anion. So we would use the ionic nomenclature rules for this. So ammonium phosphate, soluble or not soluble? Ammonium phosphate is soluble. It doesn't matter what it's attached to. It could be attached to any other anion. As long as the cation is one of these, then it's soluble. Yeah.
So that's a salt.
This is what we consider a salt. A salt is a cation. Basically, a salt is this. It's an ionic compound that's not an acid. It's a salt. This is a different name.
Most of them are solid, right?
Most of the salts are solid, yeah.
most salts in pure form are solid, you know. Like pure ammonium phosphate's a white solid. Pure sodium chloride's a white solid, but since it's easy to dissolve in water, then they'll form a liquid solution. But otherwise, they're in pure form, they're solid. There are some salts that have fairly low melting points, and it's very rare that you'll have a salt that's a liquid at room temperature. But it's possible.
There is one that I'm not aware of. The same thing goes. Sodium. Let's do another example. What is this one called? Potassium permanganate in pure form is a purple solid. This is a white solid. Is this purple solid soluble in water or not soluble? Yeah, it's solid. It's the potassium cation with the anion. Yeah. What's the anion name? Permanganate. It's the potassium cation with the permanganate anion. So potassium permanganate is soluble. Potassium is funny to spell. Potassium permanganate. Potassium permanganate. All right. So first look at the cation. Then, if it's not one of these, then the anions. So if not, then the anions. If so, then we're done. So we want to have this, and so we're going to look at this next. The first anions we're going to look at are chlorides. We want to look at acetate, nitrate, and chlorate. So what's the formula for acetate? C2H3O2. 232, the charge? Minus. Good. Nitrate? NO3, charge? Chlorate?
ClO3 minus.
Good. Well, anyway, this is not a comprehensive list, and some ions might behave similarly to some of these. Like instead of chlorate, you might have a bromate, and so you might guess bromate might have comparable properties as chlorate does. But anyway, let's continue on. These are all soluble. Okay, so let's name this. This is a white solid. Is this white solid soluble or insoluble? This white solid soluble. What is the name of that white solid? Yeah, this is lead 2 acetate. How about this one? What is this one called? Manganese 3 chlorate. Soluble? Yes. Manganese 3 chlorate is soluble. if it's not an acetate, nitrate, or chlorate, then the next group anions we look for are chloride, fluoride, bromide, and iodide. Chloride is, the formula for chloride is what? Cl? Cl2? Chloride. Well, it's tricky because the "ide" ending tells me it's got to be an anion. And so is it Cl2 minus? Is that the,
You said CO2 minus?
but the "ide" also tells us it's a monatomic. It's got to just be Cl minus. Bromide? Br minus. Iodide is I minus. What about fluoride? How about fluoride? Well, fluoride is missing on purpose. Fluorides have too many exceptions. Therefore, it is best to look these up individually, to look up individually. Let's see, is this, let's see if this finally is working now. Okay, it's still not working, so otherwise I'll show you some other time. Chlorides, bromides, iodides are soluble, except when paired with Ag plus, what do we call that? Silver ion. Pb2 plus, lead 2, and Hg2, 2 plus. It's called mercury 1. So, except when paired with silver, lead 2, and mercury 1 ions. And so that means when they're paired with these ions, we say it's going to be insoluble. And so an example would be this one, which we saw earlier. What's this called? Is that silver 1 chloride or just silver chloride? Just silver chloride. So this is silver chloride. Silver chloride, is it going to be, this is a white solid. Is this white solid going to be soluble or insoluble? It's insoluble because it's one of the exceptions. This is insoluble. And so we don't expect this white solid to really dissolve in water. Okay, let's go with another one here. PbCl4. What would this one be called? If I'm looking at PbCl4, we would call it lead 4 chloride. Lead 4 chloride should be soluble or insoluble? It should be soluble. It's not an exception. And therefore, it should dissolve. Which is weird because lead 2 chloride doesn't dissolve, but lead 4 chloride does dissolve. It's weird, but it's because of the structure. You know, if we look into the structure, then it makes more sense. You know why? It turns out that, you know, typically when you have an ionic compound like this, ionic compounds form molecules or they form lattices? They form lattices. However, lead 4 chloride is a weird one because it actually forms molecules.
It's because of the bonds, the type of bonds it has. It has something that I call more covalent bonds versus ionic bonds. We'll talk about the bonds later, so you don't have to worry about it now. You know what this one's called? SC. You know what SC is? Scandium. Okay, should we say scandium? And what's the charge on scandium? 3. Should we call it scandium Roman numeral 3 or just scandium? It's well, except for scandium and yttrium are always +3, so it goes into the. And so it actually is just scandium because there's only one charge for scandium. Right after you go past scandium, like titanium, let's go. Like that, we'll talk about that one again. But scandium chloride, is that soluble or insoluble? It's soluble. Means that solid scandium chloride should dissolve in water. How about titanium? What is this called? This is titanium Roman numeral 4 chloride. Titanium 4 chloride should be soluble or insoluble? This is soluble. And so it's just when the chloride's paired with one of these. We'll do one more here. What is this called? Hg2Cl2. This is called mercury. I know it's weird one. It's actually mercury 1 chloride. And mercury 1 chloride is insoluble. I know this is mercury 1 because chlorides are -1. And so Hg, each one has to be plus just 1. So it's insoluble. Alright, this chlorides, bromides, and iodides. The next thing we're going to look at is the
Professor, this is the sheet, right? So
yeah, that's a sheet. I'm not going exactly the same as the sheet, but similar to what the sheet was doing. 3, 4. The next one we're looking at are the sulfates. Sulfates. For the sulfates, well, what is the formula for sulfate ion? Sulfates are SO4 charged. 2 minus. SO4 2 minus. Sulfates, when paired with cations, are soluble. These are soluble except for silver ion, lead, 2, mercury 1, mercury 2, calcium, strontium, and barium. What is this called? Iron 3 sulfate. Is iron 3 sulfate soluble or insoluble? Iron 3 sulfate should be soluble. So if I have some solid iron 3 sulfate, it should dissolve in water. What is the formula for barium sulfate? barium sulfate formula. BaSO4. BaSO4, barium sulfate, is going to be soluble or insoluble? Insoluble. So most sulfates are soluble except for these. So this is insoluble. Calcium sulfate, CaSO4, same. Those are common. Calcium sulfate's a common chemical. Lead 2 sulfate, same. Insoluble. But most of the other sulfates are soluble. Unfortunately, you guys have to memorize these rules.
These are all soluble in water. So they just dissolve.
They dissolve, but you know they aren't infinitely soluble. So, for example, sodium chloride dissolves in water, but you can't dissolve an infinite amount. And so, if it, you know, there's a cutoff. The cutoff is if you can dissolve more than 0.1 moles of the substance in 100, actually in a liter, we call it soluble. If you can't, we'll call it insoluble, or if it's around 0.1, we'll call it slightly soluble. So there's a more definitive cutoff, but you know, it's just in general, you can dissolve quite a bit.
So those that are insoluble, they just remain as a solid in the...
Yes, right. They remain as a solid. So for example, 0.1 moles of sodium chloride would weigh 3.6 grams roughly, or something like that. We could dissolve more than that in a liter. But silver chloride, you know how much silver chloride you can dissolve? In a liter of water, you can only dissolve about 1 to 2 micrograms of silver chloride. So if you can only dissolve 1 to 2 micrograms in a liter, then most of it doesn't dissolve, so we call it insoluble. So insoluble means this: only a tiny, tiny, tiny bit dissolves, if anything. It doesn't mean it's infinitely insoluble. You know, it doesn't mean that 0 dissolves. It just means that, for the most part, not much dissolves. Yes.
So if you were to hypothetically put a large amount of that into water, some of it would dissolve into the water, but the rest would just sink to the bottom?
Yes,
Okay.
right. Right. And so that's correct. You know, if you put silver chloride in water, most of it will sink to the bottom, but a tiny, tiny fraction will dissolve. Correct.
So like sugar is insoluble.
Sugar is soluble, but sugar is not infinitely soluble. I can show you the solubility if I can connect to the internet, but I can't. I don't know. We could look up. Actually, what I wanted to do is I wanted to look up some fluorides to show you the variation. We'll do it next. All right, so these are mostly soluble. So what were the anions? What were the groups of anions that we started with? What was the first group of anions? Number 2. Well, that was the cations. We start with number 2. Nitrates, acetates, and chloride. And then followed by the chlorides, bromides, and iodides, followed by the sulfates. Those are mostly soluble. The next series of anions we're going to get are mostly insoluble. And so the first one we're going to look at is what? Constantine.
Oh, I'm sorry. Oxides and hydroxides.
Oxides and hydroxide. Oh, sorry. Hydroxide. We'll go with hydroxide. Most oxides are insoluble. So we'll just do hydroxides now. Hydroxides are
OH minus.
OH minus. These are insoluble.
Except,
Except group 1, ammonium, barium.
well, I don't like to go like that. I like to do group 1, ammonium, and calcium, strontium, and barium. Just down the line, calcium, strontium, barium. Are there others? So for the most part, hydroxides are pretty insoluble. So here, what we'll do is we'll do some examples here. What would the formula for aluminum hydroxide be? Aluminum hydroxide. Al. How many OHs do I need? 2?
3. Aluminum plus 3.
Yeah, aluminum plus 3, so I need 3 hydroxide. Aluminum hydroxide, is it soluble or insoluble?
That is
Insoluble. Aluminum hydroxide is insoluble. One of the most common hydroxides that we encounter is sodium hydroxide. What was the formula for sodium hydroxide again? NaOH. NaOH goes by other names, drain cleaner or lye. You can buy it at the supermarket. It's a white solid. Does it dissolve in water? Yeah, it's a group 1. So it dissolves in water. So sodium hydroxide is soluble. Okay, the next example is I'm going to do this. Barium hydroxide. What's the formula for barium hydroxide? BaOH2. 2 hydroxide. Barium hydroxide is soluble or insoluble? Yeah, barium hydroxide is, I'm sorry, what was that again? Insoluble? It's one of the exceptions. So it turns out it's soluble. Yeah. And so most of them are not, like aluminum hydroxide. What do you think about iron 2 hydroxide? Iron 2 hydroxide is soluble or insoluble? Insoluble.
So how is sodium hydroxide soluble? It's not an exception.
It is group 1. Yeah. Sodium, potassium, lithium, cesium, all those are soluble. All right, then we'll go on to the next group. Let's go to the next group now. After the hydroxides, then we have the sulfides. We also have the oxides, but the oxides, most oxides like rust insoluble. And so oxides are insoluble, but there are more exceptions here. So I don't want to group oxides there. Or fewer exceptions. So the next one we're going to look at are the sulfides. What are sulfides? Sulfide is ion is, what's the formula for that? S, yeah, with a -2 charge. That's sulfide. Sulfides are insoluble except, yeah, they're the same, group 1 and ammonium. Group 1 and ammonium are always soluble. So group 1 and ammonium. And what else? Group 1 ammonium, and it turns out group 2 now, throw on there. Group 2. And that's it. And so
what this means is, let's do lead 2 sulfide. What's the formula for lead 2 sulfide? PBS? That's correct. This is lead 2 sulfide. Lead 2 sulfide, is it soluble or insoluble? Insoluble. What's the formula for iron 3 sulfide? Iron 3 sulfide.
S32.
Yeah, that's correct. This is iron 3 sulfide. Is iron 3 sulfide soluble or insoluble? Insoluble. What's the formula for sodium sulfide? Sodium sulfide. Na2S is correct. Is it soluble or insoluble? This is soluble. So sodium sulfide is soluble. All right, just one more category left. That'll be number 7. This one will be carbonates, chromates, and phosphates. Carbonates, chromates, and phosphates. What is carbonate ion?
CO3 -2.
Chromate?
CrO4.
Phosphate?
PO4.
Yes. These are insoluble, except for group 1 and ammonium only. They're pretty much insoluble.
Professor, I don't know if they made mistakes, but they also included sulfite.
Sulfites.
Sulfite.
They didn't make a mistake. I'm just sulfites. I'm doing it based on. We aren't going to be doing that much with sulfites. No idea. I'm making my list a little bit different than the list in the book. I'm making it a little bit shorter than the list in the book. All right, so group 1 and ammonium. Let's look at some of these. All right, let's go with zinc phosphate. What's the formula for zinc phosphate? Yeah. All right. Zinc. Why isn't it zinc 2 phosphate? Why is it just zinc phosphate?
Because it's fixed.
Yeah, because it's fixed. Just memorize it. So zinc phosphate soluble or insoluble? Insoluble.
Yeah.
Calcium carbonate. What's the formula for calcium carbonate? CaCO3. Good. Calcium carbonate, soluble or insoluble? it's actually insoluble. Let's do another one. Ammonium phosphate. What's the formula for ammonium phosphate? NH4 parentheses 3 PO4. So ammonium phosphate, that's correct, is soluble. These are, we start to want to get some information from the formula. This is one of the pieces of information we can get along with others. So we'll continue this. We'll take a break right now and then continue this.